So we're going to talk about what happens to those calves early on in life as they sort of mature and enter the repro string, and then in their first and subsequent lactations. And then also some more recent analyses that we've done sort of looking at impacts of heat stress during late gestation on how long those animals persist in the herd. So I think this will tie back into some of the presentations yesterday about sort of extending out the longevity of animals in the herd, and this may be another thing to look at. So, familiar slide, since I showed this a couple of times ago, but instead of looking at effects in the cow, now we're going to focus on that calf that is heat stressed as much as the dam during that period of late gestation. We'll look at aspects of growth in those animals. We'll look at mammary development, some other physiologic traits that those animals differ in at maturity in terms of responses to acute heat stress, effects on adrenal development, some other things. We'll look at survival of those heifers, and then also the potential impact on their offspring. So the idea that this is truly a fetal programming impact of late gestation heat stress. And just to set this all up, I have to say that when we started looking at this, I didn't really think there'd be much of an effect. Thought, these calves, they're 7+ months in gestation. Shoot, calf could be born and live, and they'll survive, they'll be fine. Figured that they were pretty bulletproof at this point. We were very wrong. So first thing, again, not anything new from our perspective. This had been shown by others before. Calves that are born to a heat-stress dam are born at a lower birth weight. So part of that is going to be the fact that they're born a few days earlier. So they don't have as long a time in the uterus from a developmental standpoint. And as I already said, we've got placental dysfunction. So that's going to impact nutrient transfer, gas exchange, all of which is going to limit growth in utero. But what hadn't really been looked at was aspects of immune function. So in terms of early life immune function, this may be as or more important than the effects on birth weight. So what I've shown here are circulating IgG concentrations in calves that were born to heat-stress dams, calves that are born to cooled dams. They all got good quality colostrum within a couple of hours of birth. They were all tubed, so we know that they got the colostrum. Yet we see from day one of life, the animals that were born to a heat-stress dam, lower circulating IgG versus those animals that were born to a cooled dam, and that persists through the first month of life. There's no difference in the colostrum quality as indicated by immunoglobulin concentration from cows that are heat-stressed versus cows that are cooled. There's a difference in volume. Cows that are heat-stressed, lower volume. But in terms of IgG concentration, it's not different, and they all got the same volume. They all got 4 liters of colostrum. So when we look at apparent deficiency of absorption of immunoglobulins from that colostrum, it's significantly lower in the calves that were born to a heat-stress dam versus those that were born to a cooled dam. So the one limitation of this study was that there wasn't a difference in terms of quality from an Ig concentration standpoint, but they all got colostrum from their dams. So we know that immunoglobulin is not the only thing in colostrum. If there's some other factor that's influencing uptake that might be affected, that was a limitation of this study. So we did a second study with 2 experiments. Again, our normal model where animals are heat stressed from the time they dry off versus cooled. But at calving, instead of getting colostrum from their dam, we had created pools of colostrum In this case, it was a pool of colostrum, of good quality colostrum, and they all got colostrum from that same pool, whether they came from a heat-stress dam or from a cooled dam. And then we saved the colostrum these cows produced, saved it from the cooled dams, and made 2 other pools and fed that to calves that were born under thermoneutral conditions, under cooled conditions. So what we're trying to look for here are effects on the calf in terms of their capacity for absorption versus effects on the colostrum itself. So in terms of the first study, very consistent with what we had seen previously, calves that were born to a heat-stress dam, lower birth weight versus the ones that were cooled. Now we're starting to see these growth effects persist because we showed that those animals were still lighter at weaning. And I'll show you some data from even older animals in a couple of slides. We were also interested in looking at some other aspects of growth, in this case trying to get a sort of a gross handle on lean mass accretion because we had some other data about differences in metabolism between these animals. And the animals that were born to a heat-stress dam, shorter at the withers, about 2 weeks of age, and at weaning versus those that came from the cooled dams. And that was consistent with some of the other data that we have that would suggest that there are going to be shifts in lean mass accretion between these 2 treatments. But the growth effects, just as we had expected previously, despite the fact that the animals got colostrum from the exact same source. And when we looked at apparent deficiency of absorption, it was still reduced in the calves that were born to heat-stress dams versus those that were born to cooled dams. So just like in our other study, if she was born to a heat-stress dam, lower uptake of immunoglobulin versus the animals that were born to a cooled dam, and they all got colostrum from the same source. So that's not explaining this difference. So then we followed up with the second experiment. Just to remind you, all these calves were born under thermoneutral conditions. We didn't expect there to be any differences in birth weight. There weren't, no differences in weaning weight, so no effects on growth, despite the fact that they got colostrum from either a heat-stress dam or a cooled dam. And in fact, when we looked at apparent deficiency of absorption, it did not differ. So the colostrum is not the issue. The calf and that calf's ability to uptake IgG is the problem. And we have followed up on this by looking at gut closure, by slaughtering some animals early in life. Just an illustration of the duodenum here section. What we're looking at, the idea is that that initial enterocyte layer turns over very rapidly, and as that turns over, we get tight junction formation, which limits the ability of Igs to be transported across the gut wall. So cell death is an indicator of cell turnover, and that's accelerated in the animals that are born to a heat-stress dam versus those that are born to a cooled dam. So that process of gut closure is already running faster in the animals that are born to a heat-stress dam versus a cooled dam. And of course, the difficulty with that is that once they're born, we can't fix it. We can't just feed them more colostrum. We're not going to be able to increase that because their capacity for Ig uptake is reduced. So we've got to fix it earlier on in those animals in utero. So all this led us to think we need to look at how long these calves are surviving in the herd. Obviously, from one study, we're not going to get the numbers that we need, so we had to combine data from a number of studies. We did these studies all at the university dairy, And I like to say that we have very consistent management of our calves and young stock. That doesn't place a value judgment on it. It just says it's consistent, right? It's not necessarily good, it's not necessarily bad, but we felt comfortable there was supposed to be laughter there, just as a pointer there. A little more? Oh, okay. Anyway, so we took data from multiple years, and the patterns are all the same, year on, and it was just to increase our numbers at this first analysis is why we combined data from multiple studies. We ended up with 40 plus heifers in each group, ones that were born to cooled dams versus ones that were born to heat stress dams. Looked at some early life effects in the bulls, but really we were mostly interested, obviously, in what was happening at the heifers, particularly in this first analysis. We've subsequently gone on, and I'll show you those data to repeat this with a much larger data set. So in terms of aspects of growth, I already showed you that calves that are born to a heat stress dam, lighter at birth, they're lighter at weaning. They remain a lower body weight year of age, around the time of puberty. So long-term limitations on growth within utero heat stress. In terms of survival, we talked about immune status being disrupted or lower in those animals born to a heat stress dam, and that sort of plays out when we look at heifers that left the herd before puberty. Most of this was due to sickness. We see higher numbers in the group that were born to a heat stress dam versus the animals that were born to cooled dam, and that then obviously led to fewer of the animals from the heat stress dam making it through their first lactation versus the animals that were born to cooled dams. So consistent with those observed effects on immune status, they don't last in the herd as long, and I'll come back to that in a couple of slides. In terms of productivity in their first lactation, animals that had been born to a heat stress dam 2 years earlier and then managed identically to their herd mates that were born to a cooled dam, in this case made about 4 liters a day less milk in their first lactation. They were all cooled during lactation. They were all managed the same. They'd all been born at about the same time, calved in at the same time. There wasn't any difference in genetic potential between these two groups. The only difference was these calves, 2 years earlier, for the last 6 to 7 weeks of gestation, were heat stressed. These were not. So, in terms of management, in terms of genetic potential, none of those explained it. The only difference that we had that could possibly explain this was that difference in body weight. Right? There are known associations between body weight at calving for the first time and production in that first lactation. And our thought was maybe during that first lactation, the animals that had been heat stressed are going to have greater compensatory gain. They're going to catch up, and then maybe second lactation, third lactation will overcome this deficit. They had already caught up from a body weight standpoint. So between year 1 and 2 of life, the animals that had been heat stressed in utero had caught up from a body weight perspective. And that's actually consistent, again, with some of those metabolic indicators that we have in those animals that would say that they're going to have greater propensity for gain after puberty. But there was no difference in body weight at the time the animals calved in, and there was no difference in body weight gain during that first lactation. So probably not going to catch up in later lactations. And in fact, as I said, a larger data set. We had more and more records that we accumulated. We looked at that. We see that consistently there's about a 2-liter drag on production if a calf has been born to a heat-stressed dam versus an animal that was from a cooled dam in that first lactation, a little bit more in the second lactation, and it really starts to expand as we move into the third lactation and beyond. So we're programming those calves with that relatively brief insult of heat stress late in gestation to have a lower productivity phenotype. And we also have impacts on those animals' immune function and status as well. And we think that's probably part of why those animals leave the herd sooner. So here are the calves that are born to either a heat-stressed dam or a cooled dam. About a year less time in the herd if they have been heat-stressed in utero versus the animals that are cooled. The pattern persists in their offspring. So now we're starting to see evidence of transgenerational effects of this one insult to that calf in utero. Again, a hallmark of fetal programming, that's going to be passed on to subsequent generations. In terms of mammary development, we have now done a slaughter study looking at impacts at birth and also at weaning. There is a reduction in capacity of the animals that is visible to the naked eye at birth. So we see that the animals that are born to a cooled dam versus a heat-stressed dam, I guess I should have asked for the clouds to come down now. I'm not sure that that's as easy to see. But certainly at weaning, you can see that there's a difference in parenchyma mass in the animals that are born to a heat-stressed dam versus a cooled dam. So at birth, there's already a reduction in mammary potential in the animals with that heat stress insult late in gestation. And looking at it at the cellular level, we see lower proliferation of the epithelial and the stromal fraction at birth, also at weaning. So we have set those animals up for poorer mammary development by heat stressing them in utero versus the animals that came from a cooled dam. In terms of sort of the mechanisms behind this, we have started to look at aspects of methylation as an indicator of the sort of programming impacts. Early work we did comparing effects in the liver of bull calves, and we looked at the sort of proportion of differentially methylated cytosines between heat-stressed and cooled calves. And then we also looked at it in mammary tissue in the first lactation of animals that had been born to a heat-stressed dam or a cooled dam. And what we see is proportionally there's a very similar sort of shift across tissues and between bulls and mature cows. So their age is also very consistent differences in methylation of cytosines that may influence then the expression, the efficiency of gene expression. In terms of the bulls, probably not too surprisingly, we see a lot of impacts, particularly on immune pathways in these animals early in life. One in particular, when we looked at it, the AGER gene, this one is hypomethylated in the animals that are heat stressed versus the animals that are cooled. It is involved in innate immune function and inflammation, oxidative stress, And so this is consistent with those animals having poorer immune status when they've been heat stressed in utero versus the animals that are cooled. In terms of the cows in mammary gland, again, kind of a similar pattern in terms of the pathways that are influenced. In this case, a lot of them have to do with mammary function, but also mammary development. One that we pulled out in particular, PERK-G1, hypomethylated in the animals that are heat stressed versus the animals that are cooled. It's involved in cell signal transduction and also affects intracellular calcium trafficking. In addition, there are impacts on apoptosis, and that's consistent with the animals that are from in utero heat stress dams having greater apoptosis in the mammary tissue, so greater cell death in the mammary tissue, and lower proliferation versus those that are born to a cooled dam. So the impacts on methylation patterns consistent with what we see in terms of the productivity, but also from the phenotypes in these animals later on in life. In terms of, sorry about that. In terms of the impacts on other tissues, we've looked at this in reproductive tract tissue. Here we've got the ovaries of the animals at birth and also at weaning. And you can see that particularly at weaning, it's pretty obvious that there's a difference in ovarian development, ovarian mass, between the animals that were cooled in utero and the animals that were heat stressed. When we look at AMH, anti-Mullerian hormone, which is associated with the follicular reserve, right? The capacity for reproductive performance throughout life, it's lower early in life in the animals that were heat stressed versus those that were cooled. So there's less potential reproductively in the animals that were heat stressed in utero versus the animals that are cooled. So long-term impacts on mammary development, long-term potential impacts on reproductive performance. We also see that there are effects on skin development. In terms of skin morphology, patterns are different between sweat gland development in these animals that could be consistent with greater capacity to rid themselves of heat at maturity. And in fact, when we have looked at that, in this study, we took animals that had been born to a heat stress dam or a cooled dam at maturity, all lactating. Pretty simple design. We put them in a pen with no shade in the middle of summer in Florida. They got hot. As you can see here, their temperature elevated during the day. But as we extended that out, you see that the animals in the open symbols are those that were born to a heat stress dam. They didn't continue to accumulate heat versus the animals that were born to a cooled dam. So better able to perhaps regulate their temperature, better adapted to higher temperatures, having experienced heat stress in utero. But of course, the trade-off is that they're at a lower productivity phenotype. So not really a trade-off that we necessarily want to make. And finally, adrenal development differs between the animals that were heat stressed and cooled in utero. We see that just kind of gross aspects in terms of size, but also in the various regions of the adrenal are affected by heat stress in utero versus the animals that are cooled. We did not see acute shifts in cortisol in this study, but we think that may be due to the fact that our sampling frequency was probably not adequate to really tease those out. But there are certainly effects on adrenal development that may have impacts later in life on those animals' response to other stressors. So taking all these data together and try to bring it back to something applied at the farm level, our idea was to look at impacts of season of birth on longevity in the herd. So clearly you can't do that from a controlled standpoint, but working with a commercial dairy, actually a few commercial dairies, we got records from animals, large herds, both in Florida and California, and then looked at aspects of productivity and herd survival in animals that were born during hot season versus born during cool seasons to try and get an idea of what was happening from a longevity standpoint. So in terms of Florida, design pretty straightforward. We just took records from cows that were in their 5th through 8th lactation. So longevity cows. And we looked at animals born in the cool season versus the hot season, and I think it's pretty clear, right? You can see very quickly, animals that are born in the hot season, many fewer longer-lived cows in the herd. And that would be consistent with what I showed you from our controlled studies through 3 lactations. They don't tend to last as long. In terms of California herds, similar, not quite as great a difference, but consistent. Animals born in the hot season going to last. They're going to leave the herd sooner than animals that are born in the cool season. Probably due to the fact that there are some differences, obviously, in the impacts seasonally in California versus Florida. In terms of why the animals left the herd, in Florida, we had more of them that were actually able to be sold versus the animals that just died. Right, 2 reasons why they're going to be out of the herd. They're either sold or die. And we see that more of those animals, and maybe it was decision-making in the herd that was sort of improved or more aggressive about getting those animals off the farm. Nevertheless, they left the herd for all of the sort of normal reasons that you'd expect. Right? They weren't leaving for any exotic reason. They were out because of breeding issues, poor feet and legs, mastitis, right? All of the sort of top reasons that you'd expect animals to leave the herd. It's not like they were leaving the herd for some odd reason, but they were leaving it at a greater rate or a faster rate if they had been born in a hot season versus animals born in a cool season. In terms of California, death loss seemed to be more of a factor. Again, similar pattern though in terms of the animals leaving the herd. More of them that were born in the hotter season versus animals that were born in the cool season at any sort of lactation number. Right? They were all just leaving sooner. We don't have the exact reason why from the herds. We didn't have those records from our California data sets. But again, very consistent with the Florida data that those animals left the herd sooner if they were born in a hot season versus a cool season. So, has an impact on longevity in the herd, what season those animals are born in. So in terms of that analysis, very consistent with the impacts that we see in our controlled studies. They don't leave the herd for any different reason than we would normally expect animals to be moving out of the herd. So we think that this longevity is programmed early on, right, in utero, and if they're heat stress, that's going to have a negative impact not only early in life, but all the way through the time that animal is in the herd. And then from a practical standpoint, it may be a consideration for what heifers we keep in the herd for future productivity. And certainly this has become a factor as we look at aggressive use of sexed semen and producing beef animals from the lower end of the herd, when do we actually keep those animals and how do we manage those animals for enhancing that heifer's potential the most for productivity and performance. So just to sort of sum up this aspect, that heat stress not only impacts the cow late in gestation, it certainly has profound effects on the calf as well. It's going to impact her mammary development. It reduces her output in the first, second, third lactation. It's also going to be passed on to her offspring. So evidence of transgenerational impacts of that one insult that animal received very late in development in utero. But it has profound impacts on her productivity and health and survival in the herd for the time that she's in the herd. So with that, I want to thank students that have worked with me, in particular colleague at the University of Florida, Amanda Laporta, was there for a few years now at the University of Wisconsin with Zhao, and other folks that have collaborated on various aspects of what I showed you today, and folks that have provided funding and support for those studies. So with that, happy to take any questions if I have any time.
You do, in fact. Thanks very much. If somebody has a microphone, we got a question over here. You're going to have to walk all the way around. Sorry.
I didn't see you.
It's here in the back. Yeah.
Oh, all the way in the back. Why not?
Getting your steps in.
So, of course, Florida is an extreme example for heat stress, and there's also a very significant cost to doing this. In your opinion, where is the crossover of return on investment and heat abatement issues?
Yeah, we've actually looked at that. Our first analysis was kind of looking at the top milk-producing states in the U.S., and obviously that goes across geographies, right? The way that we approached it was to estimate the number of days of potential heat stress that we would have in any location. And that was an average THI over 68. Okay? The average for the top milk-producing states in the country was 3 months. So potential heat stress for at least 3 months of the year. And honestly, I think that that's probably an underestimate because we know that we've been having longer summers, right? Not just hotter summers, longer summers. So the next thing we did, looked at the number of cows and the average productivity, that type of thing, and made estimates. And, it all depends on costs of facilities, that type of thing. But in almost every case, it made sense to get those cows cooled during the dry period, just looking at the response in the cows. Not even looking, our first analysis, we didn't have enough data on the calves yet. When we followed up and looked at it in the calves as well, it about doubles the economic impact. So, I can get you those references, but it's kind of a no-brainer that you want to get those animals cooled pretty much everywhere, in the U.S. at least, where we would have the potential for heat stress. From Florida to the upper Midwest. Northeast, Texas, everywhere. We tend to have a misperception of heat stress, and I think that when we go from an air-conditioned house to the air-conditioned truck to the air-conditioned office, it's only hot for a couple of weeks in the summer. It's not too bad, right? She's out in the barn, and she's got a 55-gallon drum of heat production that is always producing heat in her. She gets heat stressed long before we get heat stressed. And so I think we have to take our perception of heat stress and realign it with what's actually happening in the cows, because we have a lot more heat stress than we realize.
Good. Anybody else? You're in the back. Should have almost stayed there.
Wrong guess.
Thank you very much for the talk. For those cows that it follows them a couple of years, is it possible to reverse it with cooling, and how long does that take?
So the quick answer is no. So the second part of the question is really moot, right? So you can't reverse it. We tried sort of very early on, right? As soon as the calves were born, we did a crossover study, those that had been heat stressed in utero, cooled in utero. Then we did the reverse up to weaning. No change, no effect. These are programmed into those animals. It's, again, very consistent with the sort of evidence of fetal programming from other examples that are in the literature, from humans to rats to other species.
Is it short? Otherwise, can we save it for the round table? It's fairly short. Well, let's see the answer, I guess.
No, animals still get heat stressed in Vermont.
Yeah. Thanks, Jeff. The cows that were switched, was that a split 30-30 on a 60-day dry period, or was it to mimic a far dry pre-fresh program switch? And why was the results different than the fully heat stressed, worse than the fully heat stressed groups?
So they weren't worse. They weren't different from the ones that were heat stressed the whole time. And to answer your first part of the question, it was kind of halfway through the dry period. We're looking at about a 7-week dry period, so it was in that kind of 24, 25 day. We just took half of them and switched them off. But it was not worse, it just wasn't, you got no benefit to it. But the fact that they were kind of heat stressed for only 3 weeks of the dry period, roughly, and you still saw negative impacts, says we got to do it the whole dry period.